So we'll chop the meeting about in three parts, like 1/3 to Aaron, 1/3 to reading and making comments, and 1/3 to sharing feedback comments. So if it sounds okay. So with this, I would like to give floor to Aaron. And would you like to share screen, or you want me to bring your slides up front and flip them when it is time?
I'll try and share.
Okay. Okay. Yeah. Please try, and then if needed, I will be your backup. Okay. And I'm switching off my microphone.
Okay, so the mic's still on?
Yes, your microphone is on. We can hear you.
Okay. I guess when I go to, or when I fill up the whole screen, I can't see your guys' faces. So if you have questions, just stop me talking.
Okay, let's take this protocol. So when anyone needs to ask questions, just switch the microphone on and start attracting attention.
I didn't put in a title slide, but basically what this presentation is just kind of a development of things we already computed in the group, and then using that to go beyond the absorption calculations that we normally do. So what I'm showing here is just our typical protocol for using BFT. So we use BFT to solve a bunch of equations to generate orbitals. So in this case, for my research, I do a lot of non-collinear, so there's some extra terms in here, but the important things are we get orbitals and energies for the ground state. And from those orbitals and energies, we can use transition dipoles and the dependent orbital approximation. So we can assume that different orbitals don't interact with each other. The Coulomb interactions or other types of interactions. And so for a lot of the materials that we model, they are nanomaterials. So in practice, like the electrons and holes will interact. And there's already established formalism, like you go to the Krzyzewski presentations or CSS students present, they'll usually use this thing called the Grete self-mediator equation to solve for or to describe exciton interactions.
Aaron, may I ask right away?
Yeah.
So I need your instruction on the following question. The Casida equation that you are showing in the first line, TD DFT, operates with transition density matrix only, while I wonder if beta salpeter is targeting or not wave function in the basis of two orbitals. Like what is the goal to find transition density matrix, which is referred to with the symbols x and y, or to get the wave function in the basis of occupied and unoccupied orbitals, or maybe there is something else. There is some connection between them. Can you please cover this before we go further?
So I think just from the reading that I've done, that this top equation here, this so-called Casita equation, like the formalism to compute like Coulomb interactions, like the formalism is essentially the same. It's just a difference of whether they use TGBFT, which deals with describing the response of the density, or whether they use GW calculations, which is the typical protocol for like beta salpeter. I'm not sure if that answered your question now or not.
Well, it partially answers. And let me ask Fatima and Yulun if the quality of audio is acceptable. Should we keep this way, or maybe if I'll try to project your slides and you have one voice connection, it may go a little better voice. Should we try this? Yulun supports, Fatima supports. Aaron, would it be okay?
Yeah.
Okay. Then I'll start sharing slides, and you just give me a little heads on when it will be time for. When it will be time to go on to the next slide. So please, please try to speak something that we test the voice connection if it goes okay.
So does this sound fine?
Okay, it is better. It is better. If the voice connection will be worse than usual, then we may try to speak slower.
Okay.
Okay.
So the main summary of this slide is that I won't go into too much details. You can see my mouse. Or I guess you can't see my mouse.
No.
Yeah, that's on there anymore. So essentially what we need are orbitals, which are these C and V broad kets. In the second and third equations. we need to compute this W thing, which is called the dielectric screening. And then the bottom equation is the dielectric constant. So those are the three things that VASP needs to compute to be able to solve this Bethe-Salpeter equation. And so my next couple of slides will just go over the protocol, how to compute these things in VASP. Next slide. I guess on this slide, the two main observables that we can get from the Bethe-Salpeter are that this y vector, that's like the exciton wave function. So we should get outputs, which should be where our eigenstate is a linear combination of these C and V states. And we should get eigenvalues, these omegas, which will represent like the binding energy, or you can compute a binding energy.
May I ask?
Yeah.
So what you're telling right now sounds like you are speaking about eigens. Is it so? How do you interpret y? Is it wave function or density matrix?
I guess it would be a density matrix, or you can arrange it into a density matrix.
Okay, yeah, please keep going. It's a new area for me. I'll try to clarify, but please keep going.
Okay, so those are the two main observables to try to extract from VASP in their output files. And so next slide. So the first step is like our usual protocol. So just optimize your model, then generate a healthy wave car. So those are using the normal steps that we use for when you're doing research on a model. And so we generate a healthy wave car. And then the next step is you have to generate this wave dir file that VASP will output from a calculation, and that's used as input for a GW calculation.
Aaron, I have another question. So, from your intuition and studies, how much this wave dir differs, or how much it is similar or different from the overlaps from the non-adiabatic couplings that we are computing?
I would suspect they should be the same, or relatively the same.
But we are comparing wave functions that are offset by a time step. So we are making derivative over time. And here it looks like derivative over momentum. If K stands for momentum.
Yeah, so K is momentum, so it goes along with the K indices for the orbitals. And so the way I interpret it is similar to how we compute transition dipoles. The overlap at the same time step.
Okay.
And so then this wave_dir file is used to construct the dielectric constant, and that's one of the outputs, or that's used in the GW calculation. So all you have to do this is just to make a subdirectory and then just do a single point calculation in your in-car with this L_optics equals true. And then it will output this wave_dir file, which has the same format as wavecar.
So it is not text. It is binary format that needs to be read in the same format as we read wavecar.
Mm-hmm.
I have another question.
Yeah.
So in the wavecar, in some sense, it includes only expansion coefficients of given orbital over basis functions, right? And here it looks like there are so wavecar in theory includes only 2 indices, and here it looks like 4 indices. 2 indices for orbitals and prime and n, and 2 indices for momentum. So it should be like substantially bigger than wavecar. Like if you have 100 orbitals, then this wave_dir should be same like number of transitions, 10,000. Like when you do calculations, do you see sizes of the files? Do they coincide or differ?
They differ.
So wave_dir
smaller.
Wave_dir is smaller. Okay.
Mm-hmm.
Okay.
So maybe.
Interesting. Maybe same as our oscillator strengths file. It runs over all transitions, but it includes only indices of orbitals rather than basis functions.
Can you say that again?
The file oscillator strengths that we compute in the group is typically smaller than wavecar, although it runs over pairs of orbitals, but it skips technical details of basis functions. It operates on the indices of orbitals. Maybe in this sense, this wave_dir also is smaller.
Mm-hmm. And it is like substantially smaller.
Okay.
So, yeah, I guess next slide. And so to generate this W, or the screen to Coulomb interaction, VASP generates an output file if you run any sort of GW calculation.
Mm-hmm.
And so there are a lot of flavors of GW that can be run. But in this case, this is just like like a single point calculation.
Mm-hmm.
So you feed in all of your input files that you need, and then just run a single point calculation. And so essentially you just feed in a healthy wave car and wave dir. And then if needed, you have to input a charge car as well.
Mm-hmm.
If you're doing linear. And then for the in car, you have to tell it to run GW single shot, so that's this GW0 for LGO equals GW0. And then I guess you have to tell it to do a single point, you have to tell it to do one minimization step. And then there are other parameters, so you can set the same number of bands. And then if you're dealing with a very large system, it gives you flexibility as to which orbitals to run the GW calculation on. Because these are, well, this is probably the most expensive calculation to run that I found for the model I was using.
Mm-hmm.
And so I was using probably n bands equals 100. But if you're dealing with a fairly large system, like if you had 2,000 electrons, you could tell it with this, you can tell it which the lowest energy state to use using n bands GW low. So that's like the bottom of your conduction band.
Mm-hmm.
And then n bands GW, like if you said do 16, calculate 16 energies, it will do 8 from the valence band, and then 8 from the conduction band. And so those are the main parameters to change in the in car to get this to run healthy. And then once the calculations runs, it will output these W full and W.tmp files, which contain all the matrix elements for this W that I have on the bottom.
Mm-hmm.
So I guess that's all I have for that. If there aren't any questions. Okay.
So it is Coulomb matrix element in momentum space, right?
Yes. So yeah, the variables are Q, so that's Q and G, so yeah, momentum vectors.
Okay. So it's Fourier transform of double Fourier transform of a regular Coulomb in coordinate space. Okay. Should I go to the next slide?
Yes. And so then this is the final calculation that will output beta salpeter or outputs. And so you feed in a healthy wave car to provide orbitals. You can feed in either one of the full or the just regular W files. And then a charge car if needed. for non-collinear calculations. And then it tells VASP to run the Bethe salpeter. For your in-car, you put this tag algo equals BSE.
Mm-hmm.
And then this NL equals 1 just to do the calculation ones. So you want to make sure that you have the same bands that you've been using for all the previous calculations. Otherwise, VASP just might shut down right away, or it might not start the calculation. And so you can choose the number of bands, but essentially choose the number of transitions for VASP to input into the calculation with these n bands SO, or n bands O and n bands V. So n bands O is occupied, n bands V is unoccupied. And something I didn't talk about in the beginning, but to make the calculations essentially run quicker, you can tell it to use the so-called Dankoff approximation, which removes the B matrices from the Casita equation. And that's just anti-resonance equals 0. And then the last tag to put in is, so this is an additional file that you have to request to be output. So it writes this BSE FETBAN file, and in there it contains eigenvalues and eigenvectors computed from the Bethe-Salpeter equation. Without this, it will just give transition energies, or it will only write out transition energies and then their oscillator strength.
Is it related to the root parameter in Gaussian?
I guess I'm not familiar.
Okay.
But I have an example of the output.
Uh-huh.
Slides.
Okay.
And so where to look? So if all you cared about was transition energies and oscillator strengths, those are mysteriously written out to the VASP run.xml file. So I had to hunt for those for a while, but yeah, so they put them in an odd location, but it's basically just written out as text. And then to find the eigenvalues and eigenvectors, those are in the BSE FETBAN file. And it's just from playing around with like what files to input. But you can kind of I guess have a choice of which energies and which orbitals to feed in. And so you can use a wave car. So it will read in a wave car just from a regular DFT calculation, similar to what the Krzyzewski group uses. So they use wave cars generated from HSE06. So you can use those energies and orbitals instead of a GW, energies and orbitals. And that's just a comment on how you can kind of choose or look at how different inputs affect your calculations. Next slide. And so these are, I'm just going to go over some of the results I got from just running on this small cluster. And I chose this just so the calculation would run fairly quick and wouldn't have to use a lot of resources.
We're using for- configuration to take into account that manganese is 2 plus and each of the chlorines is minus.
Yes, that's what I assume the oxidation would be.
So it will not come naturally. One needs to look what VASP is making automatically and then add additional 4 electrons. Okay, but we are not, we are looking only on procedure. Let's keep going. Even if it is not done, it can be fixed for productive results. Are we on the connection? Are we connected?
I can hear you.
Okay. Your images are frozen. Let me switch off my camera. Okay, so please keep telling the story.
So yeah, this is the model I ran it on, I guess. Next slide. So this slide is comparing a computed absorption spectra using our regular method, which is shown in this red line.
Mm-hmm.
And so that's running an HSOC plus a spin orbit coupling calculation.
Mm-hmm.
And then comparing it to the Bethe-Salpeter computed absorption spectra, which is the blue line.
Mm-hmm.
And so just from this example, you can see that the lowest energy transition became at least a couple orders of magnitude higher in intensity, and it was redshifted.
Mm-hmm.
And that follows, like numerically, like, it follows the consistent trends that you would expect.
Okay.
So that was one comparison of methodology. And then next slide. So this was just a test because in the VASP instructions, it recommends to do the calculations using an exact algorithm, which is the red line, compared to like a normal optimization, which is done with this so-called DIIS algorithm. So that's what VASP would normally run if you didn't tell it to, or if you didn't specify which type of algorithm. And so just to see what the change in the results would be, I computed this WaveDir file from both, using both methods, and just compared their spectra. And for the lowest energy transitions, the intensities are basically the same.
Mm-hmm.
When you look at the higher energy transitions, those get overestimated by a little bit, but overall it basically shows the same trends. So essentially this was just to check to see, like if we're want to do calculations for much larger systems, whether we can get away with doing a cheaper calculation.
Okay. Aaron, may I add a comment?
Mm-hmm.
So I see your explanation of this equation where we started from, and so that it corresponds to transition dipoles. And I think it has a connection to work by Fatima that she's completing right now. So originally we are speaking by when we work in the coordinate space, we replace momentum operator by derivative over coordinate. And if we are working in the momentum space, then the position operator is replaced by derivative over momentum. And if we place derivative over momentum in here, then it would correspond to matrix element of position operator, which is transition dipole.
Mm-hmm.
Make sense?
Yes.
Okay. Yep. Sorry for interrupting. Please keep going.
And yeah, just to check methodology was the main points
Mm-hmm.
for doing these calculations. So next slide. And so this is an output file, the BSC FETBAN output file from the calculation. And so it contains quite a bit of information, but I tried to label it as best as I can. And so for each eigenvalue, it'll split out a block, which is this 375. And so that's like the number of transitions that are used to compute the eigenstate. And then this 10 represents that we computed 10 eigenstates. And then below that, it just outputs column data for each eigenvalue. So this one BS eigenvalue just represents the lowest energy transition.
Okay. So this tells that lowest, and the whole table is for only one at least what is shown on the screen is only for one excited state, right?
Yes.
So all these pairs of orbital contribute to one exciton with this expansion coefficients. So it's relative contribution of each orbital pair to selected excitation. And the pair close to band gap has larger contribution.
Yes, except I think the amplitude
Mm-hmm.
is the column to the left.
Mm-hmm. Or it is a complex number with both real and imaginary.
Oh, that could be what it is. So column 6 is just the magnitude.
Okay, so it will be real square plus imaginary square. Something like that. So if we take square of these two numbers, add together, and then take square root, we should get this number. I do not feel energy to take calculator and check, but it sounds right.
Yeah, it looks. Yeah, that is incorrect.
Okay.
So I guess the only other thing is that in this line that says 1 BSE eigenvalue, to the right of it, it also provides IP eigenvalue,
Mm-hmm.
where IP is ionization potential. And so the one possible way to get a binding energy is just to subtract the IP eigenvalue from the BSE eigenvalue. Well, that's my thought anyway, but I guess.
Okay.
Not exactly sure which, if this IP eigenvalue just corresponds to, like a normal DFT, just removing an electron from the HOMO orbital.
It's a reasonable hypothesis. We may keep checking it.
So yeah, that's essentially the structure of this output file.
Mm-hmm. Mm-hmm.
And so to answer your question about transition density, I mean, it would be possible to take these particle pair columns and then plot them as a density. Or we could just plot it in a matrix with the amplitude.
Maybe there is a transition that unifies the excited states composed as pairs of electron and hole and transition densities. Let's deposit this question as a plan to answer within near future.
Okay. And so yeah, that's all I have to say about this slide.
Does it mean we go to the next?
Yeah, I guess that's the rest is just more equations.
So we do not need to go over the rest of the slides.
Right. Yeah, there's equations for how VASP computes the outputs for each calculation.
Do you want to give any comments, or it was not your plan?
Yeah, I guess I didn't plan.
Okay.
I couldn't really provide much more information than just what's written on the slides.
Okay, very good. Please join me in uploading to Aaron, and let's check if anyone has questions to Aaron. Kevin? Kevin, you don't have questions to Aaron? Fatima? No questions? Yulun, do you think this information is sufficient for reproducing this methodology for other systems? Or we need to ask Aaron to give more detailed templates?
Yeah, I guess so. So how expensive is this calculations?
So for the model I ran, it was 7 atoms. I think I put in 100 bands. So they required like a lot of memory, but the calculations went really quick.
Okay.
And so to run the Bethe, so they actually run the Bethe-Salpeter calculations. Like it needed like 512 cores, but it ran in like 50 seconds.
Okay.
So memory seems to be like the most limiting step.
I see. I have another question. So is there any other way in VASP we can just address exciton effect? I guess my question is this only way to address exciton effect in VASP?
So they don't have TD-DFT yet, as far as I know, but they do have a time-dependent Hartree-Fock. And I think it's essentially, you do the same steps, but you don't have to do the GW calculation. So you just need your orbitals and your oscillator strength from the wave dir file. But I guess I don't know if that computes. Well, it probably computes like a transition density or like an excitonic state, but I'm not sure about binding energies, how reliable that they would be.
Okay.
Yeah. Very good, very good. Thank you for finding this. It's very timely and important, and maybe we need to set up to convert these slides into more practical manual for like doing steps, and each of us may want to try to repeat this calculations. So are there more questions to Aaron? Oh, okay. I was thank you, Aaron, for typing it. I was asking, are there more questions? I was suggesting that we may want to convert this presentation into practical manual, so maybe that each group member will try to rerun similar calculations and get skills into this area. And if there are no more questions to Aaron, let's thank him once again. And I suggest we are going forward with reading. Since we spent a little more time on this presentation, let's read for maybe half an hour and then get back with comments. So if Kevin wanted to share the materials for reading, please resend email to me, because I haven't seen your materials yet in all 3 of my email accounts.
Yeah, I shared it to you like 15, 20 minutes ago. Maybe you still didn't get it?
No, please resend. Please send it once again.